Okay, so we start on page 8, and it's been a little bit disjointed because we haven't had class since last Wednesday, a week ago. Let's remind ourselves of where we were and where we're headed. So last class we talked about sequences. Sequences are just ordered lists of numbers. You have 4 colorful sequences up here on the walls, all right? Just lists of numbers. Today we introduced the very important word series. And for the next, how many classes are highlighted? For 8. The next 8 classes, we will continue to talk about series. Every class for the next 8 classes, we're going to talk about series. So this is a major theme in our class. So a couple of other things in the calendar here. Project number 7 is now officially assigned. It's called Deuce. It's on your table. So make sure you grab a copy of Project 7. That is due on April 24th. That's Wednesday next week. Oh, I was supposed to think about the project date and the quiz, and I haven't thought about it since we looked at the calendar a week ago. So I'm going to try to do something to make it so we don't have the quiz and the project due on the same day. I'll get back to you about that. Any other questions about the calendar? You can see the bottom. Isn't that exciting? Yeah. So today's class 27. Normally there are 42 classes, but we had 3 snow days, so only 39 this semester. Okay, one other thing, right, so we've got 2 quizzes left. There was another one that got canceled because of all of our snow days. There was supposed to be an 8th quiz. And then we have one more real math project that I'm going to assign. It's here on the table after the one that I just handed out. And then project 9 is reflect on the semester. So this project and then one more real math project and then the reflections project. So definitely getting there. One quick announcement. Today there is a Study Strategy All-Stars Forum happening at noon in the library solarium until 12:50. Lunch is provided. A panel of peer tutors will share their best strategies. Topics may include memorizing, maintaining concentration, reading effectively, taking great notes, demystifying the writing process, how to be disciplined about homework, managing your time, test-taking strategies, and anything else that the audience asks about. It's happening today. Are there any peer tutors in the room who are going to be part of this? Okay. All right. I'm not sure. I know that they've had this in past semesters. So check it out if you're interested. And that's that. So let's come back up here to page 7. So we'll start here with number 1, Joe. Okay, those words start SE. It can be quite confusing. We understand the difference between sequence, which is a list of numbers, and series, which is the sum of a bunch of numbers. Okay, number 2, Chris. Okay, so the series that we're going to be interested in are going to go on forever like this one does. You can see the dot, dot, dot. You're adding 1 plus a half plus a third plus a quarter forever. Now, every time you add, is the sum going to get bigger or smaller? It's going to get bigger. So on the one hand, it feels like we're going to approach what? If we just keep getting bigger and bigger and bigger? Infinity. But if you recall, we saw some integrals, some areas, I guess I should say, like if this is y equals 1 over x squared, we discovered that the area, even if you go forever, and even though every step to the right you are adding some positive stuff, what kind of a thing is true about that area forever? It's finite. We saw some very counterintuitive things here, where even though every step to the right you're adding more purple, it turns out it converges to some finite number. So it's not enough to just say, oh, it's going to go to infinity because you keep adding positive stuff. Sometimes it goes to something finite. All right, let's go to number 3, and we'll start with Tassiday. Yes. Everyone understand the pattern? 1, 2, 4, 8. In fact, where will you see that pattern in this room? 1, 2, 4, 8. It's over here in blue. This is the doubling pattern, right? Okay, so what we want to do is write out the series that represents the total number of grains of sand on the chessboard. Okay, so on the first square we said there was 1, and we're doing a total. So what operator? Plus. Second square, 2. Next square, 4. Let's do 2 more squares. 8, and then 16. And I'm going to put a dot, dot, dot because I don't want to write all the numbers, but anybody happen to know offhand how many squares are on the chessboard? It's 64. It's an 8 by 8 square, the chessboard is. If I gave this as a test question, I would include that fact in the question. So apparently we're looking for 64 numbers. How many numbers are in my blue list on the wall here? 20. So the 20th one you can see is a little upwards of 1,000,000. We're trying to find the 64th number in this list. So the question is, I mean, it's a huge number. I don't want to even write the number. I'd really like to just write a little expression that tells you how to find the number. How do you get the number in the bottom row just looking at the single number above? It's 2 to that power, isn't it? Like if you look at the 5th number here, it's 32, but isn't that exactly what 2 to the 5th is? Okay, so then maybe I can come over here and I can write that down below. So this is really 2 to the 1st, and this is really 2 to the 2nd, and this is 2 to the 3rd. Yeah, we'll use the sigma notation as well. Does the pattern continue for the very first term here, the 1? What is it? That's 2 to the 0. Yeah, so yeah, what's the last term there? I'm looking for 64 numbers in this list. It's 2 to the something. 2 to the what? The 63rd. Right? Because that first one there is the 0th one. So the 0 kind of brings in an extra, so we toss out 1 at the end. So 2 to the 63rd goes under. It's not really helpful, but I'll copy that up above. 2 to the 63rd. And that expression represents the total number of grains of sand on the board. Okay, Cole had suggested maybe using sigma notation. So let's try. Get some more practice with that. So big sigma standing for sum. The idea here is you need to write a formula for the general term, where the formula is here in green. Every one is of what form? 2 to the something. So I'm going to use I. Yeah. So I'm going to use 2 to the I, and then it follows the pattern here in green. What's the first I? 0. What's the last I? 63. So I equals 0 up to 63. So that's the very compact way to write it down. I don't know if this is going to work, but I am curious to see if Excel can handle 2 to the 63rd. Again, it's bigger. So the 2 to the 63rd is about 9.2 times 10 to the 18. Can anybody name that power of 10? Millions, billions? Yeah, it's like 18 zeros. Yeah, it's after quadrillion. It's quintillion, right? So about 9 quintillion grains of sand on that last square, which I suspect is far more grains of sand than it would take to fill the Earth, but we could calculate that. So is that the total? That's the total number of grains on the board? No, that's just the very last square, right? And then there's all the other ones. So what we're interested in here is the sum of all of these. So we'll move on to 4. Dawn? Okay, we'll pause there, and I'm going to underline this. It might be underlined on yours already. Geometric series. It's defined. That's what we're talking about today. Every term is the same constant multiple of the previous term. If you're sitting on the 8 grains of sand, how do you get to the next number? You double it, multiply by 2. If you're on 16, how do you get to the next number? You multiply by 2. That's a very special kind of series. Is this one over here the green? These are my cubes. Is this something where you keep multiplying by the same number? What do you multiply the 1 by to get the 8? Yeah, well, what do we multiply the 1 by to turn it into an 8? 8. What do you multiply 8 by to turn it into 27? Is it also 8? No, this is not a geometric series because you can't multiply by a consistent number. How about my yellow squares up here? 1 times something, 1 times what? To turn it into the next number, I have to multiply by 4. Do I multiply that by 4 as well to get to the next number? No, this is not a geometric series. Geometric series are very special things where you multiply by the same number every time. That's a good question. Why do we use the word geometric? I feel like I used to know the answer to that question. Anybody have any idea? Let me get back to you. I'm certain there's a good reason. I don't happen to remember off the top of my head. Yeah, geometrics, I think Ernie is recognizing right away that what does it mean to say you keep multiplying by the same number? Well, isn't that what an exponential does? You keep multiplying by the base. So that's exactly what our geometric series are going to look like, is a number raised to a power with a tiny bit more freedom. But that's a great observation, Ernie. Okay, Dawn, can you keep going? What's that? Good question. Can it be plus something? So what if we added 1 to all these numbers in the bottom row? So the numbers now become 3, 5, 9, 17. Yeah? Can you multiply by the same number to get those numbers? 3, 5, 9, and 17? We can't. So you're not allowed to just add. It seems easy enough, just add a little number, but it changes it. It's not geometric if you do that. Good question. Okay, Dawn? Okay, so here's what we're going to do. We're going to try to figure out what we get when we add up all those blue numbers from 1 to 2 to the 63rd. So first thing I'm going to do is give a name to that thing. I'm going to call that thing S for geometric series, for series, I guess I should say. And I'll just write out the first 3 terms, 1 plus 2 plus 4 plus all the way to 2 to the 63rd. And then we're going to multiply both sides of that equation by the common ratio. The common ratio is so named because it is the ratio you get when you take one term divided by the previous term. So let's find that common ratio here. You take, so your common ratio is equal to a term, current term divided by the previous term. So for example, if I take 16, what was the previous term? 8. What is that equal to? 2. But if instead of taking 16, I had taken 8 divided by what's the previous term? 4. And what is that equal to? 2. And so ratio, because we're dividing, common, because it's always the same. There is no common ratio for my yellow square numbers up here. It's a different number when you divide one term by the previous. So the common ratio is 2. So what we're going to do is multiply everything in this black equation by 2. So instead of calling it S now, what do I have? I have 2S equals, I should preface this and say, you could find the sum of all these things by typing in 1 plus 2 plus 4 plus all the way down to 2 to the 63rd. But that means typing in 64 things. And all I'm trying to do is avoid typing in 64 things. And we're going to do a little bit of work here, and we're going to get one nice clean formula that we can just type in one shot, one expression, instead of typing in 64 things with plus signs. Okay, so we're multiplying both sides of black equation by 2. So what does the first term now become? It becomes 2. Next one becomes 4. The next one becomes 8. I'm going to write them, but I'm going to put them jogged off by one spot. will there be a term that looks exactly like 2 to the 63rd? Yeah, so I'm going to write 2 to the 64th out here, right? When you multiply the last term by 2, you get 2 to the 64th. What will the previous thing be? 2 to the 63rd, okay? Everybody see the terms there? They just shifted 1. Everybody shifted 1 to the right. And then the next thing we do is subtract. Let's do top equation minus bottom equation. Do I want to do that? Yeah, that's right. When we subtract the right-hand sides, almost everything cancels, which is lovely. So we're going to subtract top equation minus bottom equation. So we go s minus 2s equals, and then Ernie called it. What's left when you do top minus bottom on the right-hand side? The 1 and the 2 to the 64. One of them is positive and one of them is negative. We're doing top equation minus bottom equation. What's positive is the 1, and then minus 2 to the 64. It is. Yeah, it's absolutely negative 1s. Everybody see it? S minus 2s. It's negative 1s is 1 minus 2 to the 64. And so then I can just do what to solve for s? Divide by negative 1. So s is equal to 1 minus 2 to the 64 divided by negative 1. Good. And then we can change things as Dawn suggests. 2 to the 64th minus 1. That's exactly what you get. So when we add all of those terms, we get 2 to the 64th minus 1, which is a whole heck of a lot easier to type into Excel than typing in all of those terms. Although, to be honest, if you have Excel, it's probably just as easy to do either one. But let's try up here. So let's do this the right way. So 1, 2, all the way down to, I'll make this a little bit smaller, and then I'll make it bigger. So we're going down to 64 terms, right? There. Oh, man. 1 and 2, and then 64 terms. And I swear to you, I swear I've used Excel before. This equals 2 to the that guy, 2 to the this guy, minus 1. That was our formula. So the first term was 1, the second term was 2, then 4, then 8. Yes? All right, so these are our blue numbers, except so we have the 1 in the beginning, and then 2 to the 63rd was the last guy. And so what I'm interested in, so we saw this one before. I'll make it bigger. We saw that 9.22 times 10 to the 18. That was the last square. What I'm interested in doing is summing these. Now on Excel, it's very easy. There's a button up here that you can push that says add these guys all up. This one. And so there it is, 1.844 times 10 to the 19. Now that kind of, I don't want to say it defeats the purpose, but this is very easy to do on Excel, but without Excel, you'd have to type in, like on your calculator, 64 things. Or what we can do instead is type in the one thing, 2 to the 64 minus 1. That's what we figured out, right? 2 to the 60. What are we expecting? That number. 2 to the 64 minus 1, which is kind of cool, actually. If you add, let's add, so you're going to have to pretend there's an extra number here in the front because we want something that starts with 1 and then 2 and then 4, right? So imagine over here on my blue list, there's a 1 and then the 2 and then the 4. What do you get when you add 1, 2, and 4? We get 7, which is exactly 1 less than the next power of 2, right? 1 less than 8. What do you get when you add 1, 2, 4, and 8? It's 15, which is 1 less than 2 to the 4th. And so it works. We're just extending it to the last square on the chessboard. For me, the first number is a 1, if we're just because I'm trying to simulate the chessboard thing. Yeah. All right, so let's come back to here. Here's something that we're going to see a few times. That right there is a generic geometric series. The very first term is A, just some generic thing. We're going to call A every time. And then how do you get to the next term? Well, you multiply by something. In the chess example, we multiplied by 2. In this, we're going to call it x, some generic multiplier. So a times x. But as soon as you have a and then a times x, the whole thing is done because you have to keep multiplying by the same thing, right? To be geometric, you keep multiplying by the same number, x in this case. So do we buy the ax squared as the next thing by multiplying by x, and then ax cubed and ax to the fourth until you get to ax to the, and you can see the funny n minus 1, that was like our 63, right? It wasn't 64 on the last term, it was 63. So this is what Ernie was talking about before. He said it's going to be some number to a power, x to a power. We don't have the freedom, like Cole had said, to add 5 to every number, but we do have the freedom to multiply all the numbers by the same thing, a. Okay, so that's going to be our generic geometric series. I'm not going to go through the calculation, but let me just write down what the final formula is over here. So sum of finite geometric series is equal to, so what does the formula become? It's a times 1 minus x to the, I have to think about it. I never remember this formula. 1 minus x goes down there. X to the n. A over 1 minus x to the n divided by 1 minus x. Let's just see how this, hopefully this agrees with the chessboard formula that we just figured out. If it doesn't, it's because I wrote the formula wrong. A is the first term. Get used to thinking A is the first term. What's the first term in our chessboard example? 1. 1 times 1 minus x is the common ratio. What was our common ratio for the chessboard example? 2. N is the number of terms. That's probably worth writing as well. N is equal to the number of terms. X is the common ratio. Yeah. Well, so yeah, it's a good question. Is it 63 or is it 64? Let me just write down some of these letters here. So n is always going to be the number of terms for us. A is the first term. X is the common ratio. It's 64. So here we don't have to play the game with the n minus 1. You see 63 was the last term, but that doesn't make any difference. It's really how many terms do you have? So how many terms do we have in that S, that black equation? We have 64 terms there, right? Because it was a chessboard. So in our example, we go 2 to the 64 right up there. Divide by 1 minus x. What was x? 2. Does that agree with this thing? That's exactly what we have over here, isn't it? Okay, so I'm going to highlight here in yellow. That's our first important formula for today. So that right there is the formula for the sum of finitely many terms of a geometric series. Okay, so let's move on to Andrew for 6. Okay, so we're going to send things forever. We're going to add forever. If I add up and my chessboard is bigger and bigger and bigger forever, how many grains of sand will I have in total? Infinitely many, right? So we would say that sum diverges because it goes to infinity. It diverges very badly. Not only does the sum go to infinity, but actually each term goes to infinity. So it's like really going to infinity, right? But there are some things that don't go to infinity. Looking at that highlighted yellow formula, suppose that instead of having a big common ratio like 2, which is what we had here, suppose that x was a small number. if x is a small number and you are raising it to bigger and bigger powers, remember n is the number of terms and we're trying to send n to infinity, what happens to x to the n when x is very small? Doesn't that go to 0? Like if x is 0.1, yeah, like a fraction. Like if x is a fraction. So maybe x is like 3/5. 3/5 to higher and higher powers goes to what number? Goes to 0. So then if x is small, really close to 0, then this x to the n term goes to 0. And so then I'm just left with a times 1 up on top, divided by 1 minus x. Less than 1 is good. Greater than something on the other side. Yeah, it's actually the same negative one that we saw last time. We'll write that on the next page. But n going to infinity, that circled term is the only one that has n in it. So I think we've just dealt with the problem. If x is small, and we'll write down what small means, then x to the n goes to 0. And all I'm left with is a over 1 minus x. So on the next page, I think we've got that written. Number 7. In conclusion, the sum of the infinite geometric series a plus ax squared plus, and then I've got some generic term here, but then there's the dot, 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 going forever, is a over 1 minus x. Do you see that from the formula you wrote? It's the thing in the parentheses becomes 1 as long as x is small. And here's what x is small means. It means x is trapped between -1 and 1. Because if you take negative 3/5 and you raise it to higher and higher powers, what's going to happen? It's going to head towards what number? It's going to head to 0. What does the negative do? It makes you oscillate between a positive number and a negative number, but they're both heading towards 0. Okay, so we're going to highlight this guy in yellow. That's our other important formula for today. And if x is big, meaning in absolute value it's bigger than or equal to 1, then the series diverges. Okay, so let's look at a quick example of that formula in action, and then we'll try this example with the ball. So making something up here, let's suppose that I write a few terms. Let's write these terms. 9 plus 3 plus 1 plus 1/3 plus dot, dot, dot forever. So the first thing to do is see if we can identify that this is a geometric series. If it's not, then we don't really have much to do. Geometric is the only thing we know about right now. What do you multiply by every time? 1/3. Instead of saying divide by 3, think of it as a multiply by 1/3. David? Are you talking about the ball? We're not doing the ball right now. Oh. Oh, but I made up an example that's quite similar to the ball, so let's not do that example. Let's try something different. So how about we'll start with 125 and 25 and 5 and 1 and 1/5. Okay, what do we multiply every time? What do we multiply by? Is 1/5, right? Instead of thinking divide by 5, always think multiply. You're multiplying here by 1/5 every time. So the common ratio is equal to, and even if you don't see it, even if you can't recognize it's 1/5, like if the numbers are messier than this, still it's always true that you can take a number and divide by the previous number. So for example, I can take 25 and divide by 125. Or I could take 5 and divide by 25. Any number divided by the previous number. And as long as you keep getting the same thing, you've got a geometric series. What's that? That's how you do it, is you just take every term, divide it by the previous, and you cross your fingers and hope that it's the same number. So the constant ratio is 1/5. Is 1/5 in that region? If you take absolute value, is it less than 1? Yes, it is. So what that means is that that series goes to something finite. It goes to this yellow formula. So then I'll put up here equals a over 1 minus x. A is the first term. What's the first term? 125. Divided by 1 minus the common ratio, 1/5. Any questions on plugging into the formula? It has to happen for all time. So, so I guess what you need to do is make sure that it happens for all the terms that you see. And then if you understand what that dot, dot, dot means, that you believe that it happens forever. And if it doesn't happen that fourth time, it's not a geometric series. You might be told in English it's a geometric series. Depends. All right, let's finish this up. We'll just get a plain number here. So this is 125 divided by 4/5. Yeah, so you can go ahead and do that reciprocal. 156.25. And it's quite strange because what we just did is add up infinitely many positive numbers, but instead of getting infinity, which is what our intuition maybe says, we got something decidedly finite, 156.25. So how about we do some more Excel stuff? Let's come up here and what was our first term? 125. And how do you get to the next term? You take the previous number and you multiply by 1/5. Yes? And so then as soon as I type that in as a formula, it gives me, it just says, okay, I can do that, multiply by 1/5. So that's probably plenty right there. You can see 10 to the negative 29 is very close to 0. So you're adding positive numbers, but they're just these little wisps of things. They're so tiny. And then what I'm going to do is add. So this one I'm just going to say is the first number. This one I'm going to say is up plus left. What will the next one be if this guy is equal to up plus left? 155. But the nice thing is that up plus left is something Excel understands. So now it just does all of them. And what do you see here? Let's see. It was rounding. Yeah, I mean, are we going to get to 156.25? No, but we're going to be, you know, within like tiny, tiny fractions of 156.25. So it's lying to us when it says it's exactly equal, but that's just because it doesn't have enough precision to tell me what it really is. It really is this number with a few more nines every time you go down. Dawn, does that help you understand the, yeah. Okay, other questions on that? Okay, let's come back here. All right, so there's this ball example. We're going to skip the ball example. Let's jump down to number 9. Okay, so in number 9, we'll go to Maggie.
It's to be repaid. Oh, sorry.
Okay, so let's take a look at point 18, 18, 18 forever. Want to write that as a fraction. Okay, so first thing we're going to do is write it as a series, as the sum of a bunch of terms. So the way we're going to break this up, we're going to say it's 0.18 plus 0.0018 plus, how many zeros here? 4 zeros. That's an 18. So do we believe we can split those 18s off? And it goes forever. And then, well, that's a series because it's an infinite sum. is this a geometric series? Do we keep multiplying by the same thing? Yes, we do. We keep multiplying by 1 over 100. That's our common ratio. So the common ratio is 1/100th. Right, that's how we're going to get 2 extra zeros every time. And the A, what's the A? 0.18, that's the first term. And we're going to use our formula, the A over 1 minus x, but before you do, you need to make sure that the x is close to 0. Right, up here, highlighted or circled in red. Absolute value x needs to be less than 1. Is it? Yeah, 1 over 100, definitely less than 1. So we're allowed to use that formula. And I stress that you need to check that because you can plug into that formula even if x is too big, and the formula is not going to tell you anything. Formula will give you a number, right? It's not going to tell you, there won't be a clear indication that you're wrong. It's just going to give you a number. So make sure x is small enough before you use the formula. So this guy equals the blue thing. So what goes upstairs? 0.18, that's the A, over 1 minus x, 1 minus 1 over 100. Okay, so we're going to clean this guy up. We can do this without calculators if we go to decimal land. 1/100th is really what decimal? 0.01. So that's 0.18 over what decimal? 0.99, which is really, just move the decimal points 2 to the right, top and bottom. Right, multiply top and bottom by 100. What's that, Josiah? 2 over, oh yeah, this guy does reduce. 2 over 11. Any questions on that one? It's confirmed on the calculator, 2 divided by 11. Okay, part B. Part B is gonna upset some of you. Let's try. Okay, this equals, so first we split it up into the repeating parts. So what is it? 0.9 plus 0.09, 009 forever. A over 1 minus x. How much is the A? It's 0.9 divided by 1 minus, what's the ratio? It's 0.1, right? You keep multiplying by 1/10 or 0.1. Is 1/10 small enough that we can use the formula? Yes, has to be less than 1. It is. So this is 0.9 over 0.9, which is 1. So oftentimes, you know, when somebody wants to show off, you know, what's the biggest number that's less than 1? Well, 0.99999 forever. What is 0.999 forever? It's 1. It is exactly 1, no more and no less, and that is quite disturbing to some people. If you give me 0.9 and there are 100 nines there, okay, that's smaller than 1. But if there are infinitely many nines there, it is exactly equal to 1. And I can maybe convince, if there are doubters, I can maybe convince you. What is 1/3 as a? And it's not infinitely many nines. It's a good try, though. What is 1/3 as a decimal? 0.3 repeating, right? People have no trouble with that? Yeah, everybody's comfortable with that, right? Okay, triple the left-hand side, what do you get? When you triple the left-hand side, 1. When you triple everything on the right-hand side, it's the same. They're equal. All right. So let's have you guys try the group thing now. So we've got about 30 minutes. I think that's enough time to get through. Let's see if we can work through on the next page. If you finish early, there are some challenge problems that we skipped. So let's see how far we can get.